Very good morning to all. In last class, we have seen about linear variable differential transducer or transformer and its working. And today we are going to see about rotary variable differential transformer or transducer, that is RVDT. And the principle and application is going to be same as that of your LVDT, whereas the difference is only in the construction. That is, the construction or operation is going to be take place in an angular manner. That is, it is going to measure the angular displacement rather than the linear displacement. Why? Because the construction is constructed based upon the measurement of your angular displacement. And here is a diagrammatic representation, and this is the only difference what make your LVDT as RVDT. The core is a rotating core that is placed between the primary winding and secondary winding. And when the core is rotating in a clockwise direction, then there will be the increase in the output voltage of one phase. And when the core is rotating in an anti-clockwise or counterclockwise direction, there will be an increase in E naught in the opposite direction. That is, the value will be negative. That is what it is meant to say. And this is what about rotary variable differential transformer. Otherwise, the principle and operation is going to be similar as that of your LVDT. And coming next to capacitive transducer, the principle of operation is based upon the familiar equation of capacitance of parallel plate capacitor. We have seen the equation of parallel plate capacitor, where your capacitance C is denoted by epsilon into A divided by D, where this epsilon is equals to epsilon naught into epsilon naught. That is, your epsilon is nothing but permittivity. The permittivity is equals to product of your permittivity of free space into relative permittivity of a dielectric. So your equation will become C is equals to epsilon into epsilon naught into A divided by D. So where A is equals to overlapping area of plates, its unit is meter square, and D is distance between the plates and its unit is meter, where epsilon naught is permittivity of spaces, as I said earlier. Epsilon naught is equals to 8.854 into 10 to the power minus 12 farad per meter, and epsilon naught is equals to relative permittivity of the dielectric. And from this equation we can understand that your capacitance is directly proportional to permittivity and directly proportional to overlapping area of plates and inversely proportional to your distance between two plates. So by varying these quantities, the capacitance is varied and it is converted into electrical energy. So the capacitive transducer works on principle of change of capacitance caused by, as I said earlier, we are going to change the value of capacitance which is caused by change in overlapping area, which is directly proportional, change in distance which is inversely proportional, and change in dielectric constant which is directly proportional. And the capacitive transducer, first by variation of overlapping area, how it is going to be varied, we are going to see. See in this equation, capacitance is directly proportional to area of overlapping area. So the capacitance changes linearly with the change in area of place. So this is the diagrammatic representation of your capacitive transducer. There will be a fixed metal and there will be a movable tube, that is core, which is going to move inside this fixed metal block, and the output voltage is measured between these two terminals. As the value as it moves towards the left side, the value of capacitance increases. Okay, as it is going to move towards the right side, the value of capacitance is going to decrease, whereas at the midpoint it is going to be at null position, similar that of your LVDT. And this is what your core type of capacitive transducer, and this is a plate type of capacitive transducer, where there will be two plates, one is fixed plate and the other one is movable plate. And when this plate is moved towards and away from the fixed plate, the value of capacitance is going to increase or decrease. That is what is mentioned here. And as we said earlier, the output is going to be linear. Why? Because the value capacitance is directly proportional to the area of overlapping area. So and this is the voltage. This voltage denotes that there is a zero displacement, there will be increase in voltage. This voltage is denotes that residual voltage what we have seen earlier. And coming to next slide, for a parallel plate capacitor, the capacitance is same formula, epsilon A divided by D. So here we are adding a distance, that is your A is denoted with x into W, where your x is the length of the overlapping portion of plates and W is width of overlapping portion of your plate. And sensitivity, we have already studied about sensitivity in previous unit, so which is equals to your change in capacitance with respect to change in distance, which is equals to epsilon into W, that is width of overlapping portion divided by distance, and which unit is farad per meter, where sensitivity will be constant, therefore it is going to give linear relationship between the capacitance and displacement. We have already seen the graph for it. And this transducer will measure the displacement from 1 millimeter to several centimeter, and accuracy will be up to 0.01%. And this is about capacitive transducer. And another capacitive transducer is cylindrical transducer. We have, first what the capacitive transducer we have seen first in the diagram. And for that, the equation, capacitance equation will be 2 pi into epsilon x divided by log of d2 divided by d1, where x is the length of overlapping area, and d2 is inner diameter of the outer cylinder, and d1 is outer diameter of the inner cylinder. So with the help of this, we can find the sensitivity with respect to change in capacitance value with respect to the change in length, which is equals to 2 pi epsilon divided by log e into d2 divided by d1. So its unit is farad per meter. And the maximum value of capacitance, where your maximum value of capacitance occurs when epsilon A divided by D, which is equals to pi epsilon R square divided by 2D. This at this area, your maximum value at this limit, your maximum value of capacitance will occur, and capacitance at angle theta is given by C is equals to epsilon into theta into R square divided by D. That theta is the angular displacement. Why? Because we are talking about the cylindrical capacitive transducer. Here the sensitivity will be equal to epsilon R square divided by 2D. And in cylindrical transducer, there will be one fixed plate, then the another movable plate. That is, the outer part is going to be the fixed part, and the inner part, what is present inside the hollow cylinder, is going to be the movable part. And as the angular displacement changes, the effective area between plates will change, the capacitance. Therefore, and one more thing, your maximum capacitance will occur at the degree of 180 degree. And this is the movable capacitance, where this is the fixed plate and this is the movable plate, and the displacement, the angular displacement, the change of capacitance with respect to angular displacement is also going to be very linear. And capacitive transducer, by variation of distance between the plates, while changing the distance between the plates, how your capacitance is going to vary. We know your capacitance is inversely proportional to the distance between the plates, that is dielectric. So it will be non-linear. So at the initial value, the capacitance, when displacement is equal to 0, the capacitance will be very high, whereas as the displacement goes on increasing, the capacitance value will fall off. And this shows the capacitive transducer by variation between the variation of distance between the plates. And as I said earlier, this here is the construction. It consists of one fixed plate and one moving plate. And when plate moves towards the fixed plate, the capacitance increases, and the plate moves away from the fixed plate, your capacitance decreases. And this change in capacitance is measured with the help of AC bridge circuit or oscillatory circuit, and then it is converted into electrical output. And the output curve is obtained is non-linear, as we have seen the graph. And sensitivity, coming to sensitivity, it has high for initial portion of the curve. So at the initial portion of the curve, the sensitivity will be very high, and so the transducer can be used only for measuring extremely small displacement. So the transducer can be used when the sensitivity value will be very high. So here the sensitivity will be high only at the starting position. So this transducer can be used only for measuring extremely small displacement. And coming to capacitive transducer of differential arrangement, that is, this arrangement is made to achieve the linear characteristics of the capacitor, that is your angle between the curve between the displacement as well as the capacitance. It has three plates, whereas in previous cases we have seen only two plates, one moving plate and one fixed plate, where here we have three plates, that is two fixed plates P1 and P2 and one movable plate here. So it forms two capacitors with differential output. So it is going to form a two capacitor with differential outputs. So the formula is going to be same for both the capacitors, that is epsilon naught A divided by D, and the AC voltage E is applied to across P1 and P2, and the difference of voltages across two capacitors is measured. That is, we are going to apply voltages between these two fixed plates, and while moving this movable plate, how the capacitance vary we are going to see. And here's the diagrammatic representation. These P1 and P2 are the fixed plates, and here is a movable plate, and the it is connected to the your voltage AC voltage E as in the definition. So it is connected to the AC voltage E, and this difference between movable plate and fixed plate is going to form capacitance 1 and EMF induced 1. And here for plate 2 it is C2 and E2, and this is the differential arrangement of your capacitor, where when M is in the midway, that is when movable plate is in the midway, the value of C1 will be equal to C2 and your E1 will be equal to E2. This is similar to the equation what we have seen for your linear variable differential transducer. So E1 is equal to E2 says that it is the voltage is equally shared between two plates, that is equals to E divided by 2. So voltage across C1, E1 is equals to E divided by 2, and voltage across C2, E2 is also equal to E divided by 2. So differential output when the movable plate is in the midway is change in your E1 minus E2. So as it is differential output, we are going to find the difference. So E1 minus E2 is equals to 0. Now, as you remember your LVDT operation, it is going to be so similar. So let movable plate is moved up to a displacement of x. We are going to move the plate for a distance x, which is not in the mid region. So the value of C1 will not be equal to C2. So C1 is equals to epsilon A divided by D minus x, and C2 is equal to epsilon A divided by D plus x. That is, this x denotes it is moved away from the mid region, and it is this shows that it is moved. As the value as the plate moves upward, the distance from the mid region is being added. That is what he mentioned here. It is being subtracted. It is mentioned here. Therefore, your E1 is equals to E into C2 divided by C1 plus C2. This formula already we know. So the value of EMF generated at plate 1 is equals to we are going to substitute the values of C2 and C1. Finally, we get value D minus x divided by 2D into E. So E1 is equals to D minus x divided by 2D into E. Similarly, if we solve for the value of E2, the formula is E into C1 divided by C1 plus C2. So E2 is equals to D plus x. Here you obtain the value plus x divided by 2D into E. That means that your value, the movable plate is in the C1 region, and that is why it is being added with the distance. And the differential output voltage is E2 minus E1, so we are getting the value D plus x divided by 2D into E minus D minus x divided by 2D into E. So del E is equals to x by D into E. So the output voltage varies linearly if you are going to operate with this principle, and the value of sensitivity is given by change in voltage divided by x, and that is this length of your that movable plate where it is moved. That will be equal to E divided by D, that is distance. So the differential method can be used for the measurement of linear displacement between your 0.01 micrometer to 10 millimeter, the accuracy of plus or minus 0.01%, and this gives the your operation of your differential transducer. And the advantages are listed here. We'll see advantages and disadvantages in the next lecture. Thank you.